So good afternoon, everyone. It's my great honor to stand here today. I'm Yixuan Li. I'm currently a research associate in the University of Bristol. Before that, I finished my PhD in the City University of Hong Kong. So today, I'm going to present my previous work on the AI-generated image quality assessment in visual communication. I'll focus on what quality means for this scenario, why traditional IQE metrics are often insufficient, and what practical insights we got from this work. Let me start with the background. So in this talk, visual communication refers to using visual content, especially the images in this work, to deliver information and influence human perception and even behavior. So in industry settings, this is typically seen in advertisement creatives where the visual is designed to achieve a specific goal. For example, attracting attention, improving understanding, or building trust. So visual communication is not only about whether an image looks good, but whether it communicates the intended message effectively to the target audience. So nowadays, AI-generated advertising content is already showing measurable impact. Here's a study from NYU. It reports that the click-through rate of advertisements generated by AI is 19% higher than those produced by humans. So this suggests that AI-generated visuals are feasible and competitive in real marketing outcomes. And it's also becoming feasible through the commercial tools, the platforms such as Amazon advertisement, Google advertisement, and Creatify AI, and something like that. So AI is making advertising production more accessible and efficient for a broader user base. But when content generation becomes easy, quality control becomes the bottleneck. So these are AI-generated advertisements collected from the social media with diversified user complaint. We can see that in real visual communication scenarios, there's an important gap. The generation quality is still not consistently controllable. So to evaluate the quality, can we directly use traditional IQA here? So in classical image quality assessment, we often focus on technical distortions like blur and compression artifacts. However, for the AI-generated image visual communication, technical quality is only a small part of the story. So many real failures are not traditional distortions. Instead, they happen at the level of a communication. For example, like text-image alignment, aesthetics, rationality, and emotional interaction. So therefore, we introduced the first AI-generated image quality assessment dataset specifically targeting real-world visual communication scenarios. So in the following time, I will introduce the details of dataset components, the specifically designed efficient annotation method, and our experimental results. So our focused advertising scenario covers both commercial product advertisements and public service announcements. So we ensure that the data diversity along 4 axes, the topic, emotion, the content promptings, and generation model. So we emphasize 2 aspects of quality, the information clarity and emotional interaction, which are very specific and unique in the visual communication scenario. So to support this, we generate 2.5K images with 5 AI generation model, where 500 diversified prompts are used to control the semantic content of image generation. So these images are created under 14 advertisement topics such as safety and healthcare, and it spans 5 emotional categories, including the amusement, such as amusement, awe, contentment, excitement, anger, and disgust. So the example images at the bottom illustrate how prompts are designed with both semantic content and emotion. For instance, in the first row, the text prompt describes popcorn kernels forming the shape of mountain, and the target emotion is amusement. So then in the second row, the prompt is about a fired electrical cord causing a small fire, and the target emotion is fear. So in this data set, we are not only generating objects, but generating content that is intended to communicate a specific message and a feeling, an emotion. So after preparing the images, the next step is to label the quality of the two aspects. As previously discussed, in visual communication, quality is not only technical. So we focus on information clarity and information interaction. But these two aspects are not easy to be quantitatively measured with specific numbers like 1, 2, 3, 4, 5, like what we do in conventional IQE datasets. So as such, we ask human raters to do pairwise preference comparison on the two quality aspects above. So to keep it scalable, we use unsaturated comparisons to save human labor. In practice, only about 40% of all possible pairs are compared by humans. So many pairwise ratings are missing in the current state. And then we use the MAP estimation with Thurston's case V model to infer the global preference scores from these incomplete comparisons. So in this way, a limited number of pairwise judgments can be converted into a global quality score for each image aligned with communication goals that we defined. So after obtaining the scores from the unsaturated comparisons, we need to verify the reliability and the effectiveness of the MAP estimation. So we compare the correlation between the scores estimated from a subset of the exhaustive pairwise comparisons data and the true scores obtained from through the pairwise comparisons. Specifically, we selected 250 images generated from 50 prompts in the AIJIVC dataset. So in each round, each image was randomly paired with another image within the same prompt. So we repeated this process for m rounds and calculate the accuracy of the preference choices derived from the estimated ranking scores. So in the shown picture, we can find that the estimated preferences can recover the true preferences after 4 rounds of comparison. So in our subjective experiment, 20 participants are employed to label 2,000 pairs randomly sampled from the whole AIJIVC dataset, which reduces the required number of exhaustive pairwise comparisons by 60%, while still preserving the same preference reliability. So here we provide a visualization of the estimated preference probabilities in the dataset, where the SRCC and PRCC between the preference probabilities for information clarity and emotion interaction. We can see that they reach a very high level, more than 0.9. So therefore, we can find an intrinsic correlation between information clarity and emotional interaction on the large dataset scale. After constructing the dataset, we evaluate the performance regarding information clarity and emotional interaction on the dataset. We report the accuracy alpha. It means the ratio of image pairs correctly predicted compared with human ground truth. And the correlation measures how well the model's predicted preference align with human ratings. So from the results in the table, we can observe that even though these IQ measures are specifically designed for AI-generated images, they still struggles on our dataset, especially the EI dimension, the emotional interaction dimension, which is harder than the content part. So among the tested models, we can see that the peak score model is the strongest baseline, but even it is far from satisfactory. So especially in the EI dimension, which again indicating the particularity of the visual communication scenario. And also, we evaluate popular large multimodal models on the proposed dataset. We, aside from the prediction accuracy, we also predict consistency. So the consistency is specifically designed for the large models, LLMs. It measures whether the model's decision is stable when we swap the order of the two input images. So a higher consistency means the model is less sensitive to presentation order and behave more robustly. So the main result in this table we found is that most open large models, actually the GPT-4o is closed sourced, they perform relatively poorly on this preference prediction setting. So often worse even than the conventional metrics designed for AI-generated images in both the IC and EI dimensions. So a second consistent pattern we found is that model evaluates EI is more challenging than IC for both quality assessment models and large models. So we included more results and experiments in the paper. If you are interested, we invite you to refer to the full version. So here we give some takeaways for this work. Generated image quality in visual communication should consider more than visual fidelity, such as whether the image clearly conveys intended information and elicits the intended emotions for a target audience. And the second one is the proposed AIGI-VC dataset provides a real-world advertising benchmark with diverse topics, emotions, semantic content, and generators, and successively challenges current IQA methods. And the third one is existing metrics and models are not sufficient in this aspect, especially for emotion evaluation. And thank you, and I think that's all for my presentation.
Yeah, I have. Thank you for your presentation. I have just two questions. So first one is, how did you come up with the categories for the emotions? Like, what was the thought process behind those, the 8 categories that you came up with?
Well, actually, for the emotion categories, we directly adopted the one of the most popular scheme from psychology, I think.
Okay.
It's the 7 emotion scheme from psychology.
Yes.
Okay.
It's mostly negative for some reason. It's not
Yeah, we didn't.
positive emotions, but those are considered the 7 basic.
But I think she has like 8 amusement.
Yeah, 8.
Okay. My next question is specifically for the LMMs part. So, what was the prompt that you used when querying for the quality score or when querying for the preference score? What was the exact prompt you used?
Actually, the prompt is as shown in this image. We first decide the content and then decide the emotions, and we use large language models to combine them together as an entire sentence. For example, the prompt like popcorn kernels forming the shape of a majestic mountain in a natural landscape. We feed this prompt into diversified image generation models like stable
Sorry,
diffusion.
I'm asking about the LLM as a judge, basically, when you are using that. The last slide,
Oh,
basically.
sorry.
Second last, yeah, here.
Yeah.
What was the prompt that you are using for them to do the evaluation?
You mean the evaluation?
Yeah.
For the evaluation, we use the same prompting that used for human subjects. Here, which image better conveys the content described in the prompt, like this. Yes.
Thank you.
Problem.
Any other questions?
One short question. So in the tables that you show, I guess you are showing the correlations. Am I right? Are those correlation values?
Yes.
The scores that you have over
The linear correlation.
linear correlation.
Beta.
So kind of one comment is that linear correlation, doesn't take into account the noise in the subjective data, because subjective data, obviously, you cannot measure it perfectly, and sometimes the order for the two images that are very close in subjective scores, you will not obtain very accurate ground truth information. And I wonder whether there's a way to better represent those scores that would ignore the conditions that are very close together on the subjective score.
Well, actually, we don't. In practice, in evaluation, we don't ignore such very minor, subtle difference. We regard them as different quality level, and we believe it can reflect the true perception of crowdsourcing, because we got the scores from crowdsourcing. And aside from the linear correlation, we also use the accuracy. It computes the proportions of pairs that are correctly predicted by the model. So I think the subtle difference, we don't consider the subtle difference as noise. And for fine-grained evaluation, we use the accuracy to amend the disadvantages of linear correlation. Yeah, that's why we reported two results.
So thank you very much. So I have a question about the reconstruction, because as far as I know, you have this random sampling the pairs, and then you reconstruct the scores, right? So, but it is not clear to me. Like it's reconstruct based on the category. I mean, you have different category, right? So, okay, emotion with this kind, or the entirely all of this. You compare all the contents, cross content comparison.
We when constructing we do the cross content under one emotion category.
Okay, so you did cross content comparison.
Yes.
But in this case, how are you going to to get a preference about this? I mean, you have to put this prompt and also the image there.
We first we use a candidate subset, and we make we pair them up. So from those pairs, we randomly select evenly from each emotion category. And in practice, we can, after crowdsourcing, we can get a probability vector. So the probability vector is two-dimensional. The first element denotes the probability that the human think the first image is better than the second one, and the second element denotes vice versa. So after doing those comparisons, we unite them into a matrix. That, for example, if we sample like n images is an n multiplied by n matrix, and we use the Thurston's case-V model to aggregate.
Yeah, so it just feels like if you cross content plus these prompts, it would be very challenging.
Yes.
To get correct ratings.
Yes.
Subjective ratings.
Yes.
Yeah.
Yes.
Okay, there's no more questions.
Okay.
Thank you, Yixuan. And we've got another coffee break until 3.
Thank you.